One person on a suspended trail bridge. The deflected shape is two straight lines meeting under their feet. You can work that out in a minute, and the answer at midspan is PL over 4T, 31 millimeters. Move them, and the tent moves with them. Now a real load. A group bunched near 1/3 span, scattered walkers elsewhere, nothing that has a formula. The standard move is to start again. Integrate the differential equation, match constants, apply the boundary conditions, and hope the load is nice enough to integrate. You don't need to. You already solved this problem. The tent you drew for one walker contains the answer for every possible load on this bridge, and getting it out is a single integral. That tent has a name. Green's functions. One solution that contains all the others. Before we can define what we want, we need the delta function, and I want to be straight with you about what it is. It is not a function. There is no function that is zero everywhere except one point and still integrates to 1. If you were told it's a spike of infinite height, you were told something that cannot be made rigorous. What it actually is a limit of a sequence, and more usefully, a rule for what happens under an integral. Watch the bumps. They get taller and narrower and eventually ridiculous. But look at the number. Integrate any of them against a smooth function f, and you get something that converges to f evaluated at the center. That convergence is well behaved even though the bumps are not. So the delta is defined by what it does, not by what it looks like. The integral of delta times f is f at the point. That is the sifting property, and it is the entire content of the delta function. Objects defined by their action under an integral are called distributions. That is a real branch of mathematics, and we are not going to develop it here, but you should know that the hand waving you were given has a rigorous replacement, and this is the door to it. Here is the problem. A linear operator L acting on y equal to some load f, with the ends held down. Instead of solving that, solve a different one. Put a single unit impulse at position 11 and find the response. Call it g of x, 11 the response at x to a point source at 11. Then here is the claim: the solution for any load is the integral of g against that load. Why that's true is nothing more than superposition, run continuously. Chop the load into slivers. Each sliver is approximately a point load, of size f of 11 times d11. The operator is linear, so the responses add. Every sliver contributes its own tenth, and the tenth sum. Take the limit and the sum becomes an integral. That is the whole idea. Everything remaining is working out what g actually is. G has to satisfy 4 things, and 3 of them are obvious. 1. Away from the source, there is no source. So L of g is 0 on each side of 11, separately. 2. G satisfies the boundary conditions, because y does and the load doesn't touch the ends. 3. G is continuous at 11. A point load doesn't tear the cable. The fourth is the one that gets hand-waved, so let's actually derive it. Integrate the defining equation across the source, from 11 minus epsilon to 11 plus epsilon. On the right, the delta integrates to exactly 1, by the sifting property we just established. On the left, the integral of g double prime is the jump in g prime across the source. Every other term is continuous and vanishes as epsilon goes to 0. so the derivative jumps by -1/t. Look at what that means on the tent. Two straight segments, two different slopes, meeting at the source. The difference between those slopes is not an artifact of the drawing. It is the point load. -1/t, at every source position, exactly. For the cable the operator is -ty double prime, so the homogeneous solutions are straight lines. Pick y1 to satisfy the left boundary condition and ignore the right. That's just x. Pick y2 to satisfy the right and ignore the left. That's L minus x. Use y1 to the left of the source and y2 to the right, each with an unknown constant. Continuity and the jump give two equations for those two constants. And out comes G, left of the source x times L minus 11, over TL. Right of the source, the same expression with x and 11 swapped. Which is the tent from the opening shot. We have now derived it, and more importantly, we know it is the only thing it could have been. First, a sanity check. Feed a uniform load through the integral. Out comes Wx times L minus x, over 2t, the parabola, exactly the closed form answer. Midspan, WL squared over AT. Nothing new, but nothing broken. Now the load that has no formula. On our 60-meter span with 360 kilonewtons of cable tension, the green integral gives a maximum deflection of 461 millimeters at 23.4 meters from the abutment. To check it, solve the boundary value problem from scratch. Finite differences, 800 nodes, assemble the tridiagonal matrix, run the Thomas algorithm. Completely different method, no Green's function anywhere. They agree to 5 parts in 10 to the 13th. That is round off. They are the same answer. And notice what the two calculations cost. The finite difference solve has to be redone for every new load case. The Green's function was computed once. Every load after that is an integral. One caveat on the model. -ty double prime equals W assumes the cable's tension doesn't change much as it deflects. Our 460 millimeters is about 9% of the 5-meter sag, which is comfortably inside that. Push the load much higher and the real cable stiffens nonlinearly, and superposition, the entire foundation of this method, stops applying. Look again at the formula. Swap x and 11 and nothing changes. G is symmetric. Stated physically, that is startling. The deflection at 15 meters caused by a load at 43 meters, and the deflection at 43 meters caused by the same load at 15. Not approximately. Identically, the same 11.8 microns per newton, both ways. Structural engineers have a name for this. It is Maxwell-Betti reciprocity, and it is taught as a theorem about structures, proved with virtual work. It is the symmetry of the Green's function. Every self-adjoint operator has it, which means reciprocity is not a fact about beams and cables. It is a fact about a class of differential operators, and structures merely happen to belong to it. The same symmetry appears as Betti's theorem in elasticity, as reciprocity in acoustics and electromagnetics, and as detailed balance in diffusion. One property, many names. One more relabeling, and this one is worth the whole video if you do structures. G is a function of two variables, so it's a surface. We have been slicing it one way, Fix the load position, look at the shape. That's the deflected profile. Slice it the other way. Fix the point you're measuring, and vary where the load sits. What you get is a plot of response at one location as a function of load position. That is an influence line. Structural engineers draw them constantly to find the worst position for a moving load, to place vehicles on a bridge deck for maximum moment. They are usually presented as a construction, a recipe with rules. They are a Green's function, sliced along its second argument. And the symmetry we just proved is exactly why the influence line for deflection looks identical to the deflected shape, a fact usually stated as the Muller-Breslau principle and rarely explained. Finally, the condition nobody mentions. Change the operator slightly, add a term proportional to y. Now sweep its coefficient. The Green's function has a denominator, and at particular values that denominator hits 0. Those values are the eigenvalues of the homogeneous problem. At k equals n pi over L, the homogeneous equation with 0 boundary conditions has a non-trivial solution. The system can deflect with no load at all. That is resonance, or in a static problem, buckling. And when that happens, no Green's function exists. Not it's hard to compute, it does not exist, because the solution to the original problem is either non-unique or doesn't exist either. The precise statement is the Fredholm alternative, either the homogeneous problem has only the trivial solution and G exists uniquely, or it doesn't and you need a modified Green's function with a solvability condition on the load. If you have ever had a boundary value solver return garbage near a critical load, this is why. The method didn't fail. The problem stopped having an answer. One last observation, because it sets up the next episode. Our operator had constant coefficients, and on an initial value problem that means the response to an impulse doesn't care when the impulse happens, only how long ago. Put that into the superposition integral and it becomes the integral of g of t minus tau, times f of tau. That is a convolution. And that single function g is the impulse response. Green's function, impulse response, convolution kernel, transfer function in disguise. 4 names, 1 object. Next time we take the transform that turns convolution into multiplication, and the whole thing collapses into algebra.